All right, so last time we were talking about degrees of freedom in SET, and I drew these two pictures and emphasized to you that the difference between these two pictures is really where the degrees of freedom live in momentum space. So this is the P minus P plus plane. And unlike most effective field theories, in this effective field theory, we have degrees of freedom that have to be identified by two variables rather than just one. So we need two variables to say where collinears are or where softs are. And there was generically, I said, a dependence on the process. So SET, or what degrees of freedom you need, depends what you're studying. Okay? And it's generically not the case that these two effective theories that I wrote down for you will describe every possible process. That's, in fact, SET, of course, won't describe every possible process. So what effective field theory you need depends on what you're looking at. It just turns out that these two sets of degrees of freedom that I wrote down to you do describe a lot of different processes, and that's why the language of SCT1 and SCT2 is useful. But there's no guarantees. You could run into a process that requires more degrees of freedom, and there are examples of processes that require more degrees of freedom than this. But this is still a useful starting point, and this is where we'll start. And then we were talking a little bit about fields last time, and one thing I derived for you was that the collinear field has a power counting that makes it scale like lambda. And then near the end of lecture, this is the collinear quark. And then at the end of lecture, we also derived a formula for the collinear gluons. So if we write down components of the collinear gluon, plus, minus, and perp, we'll remember what these notation means. This means n dot A, and this means n bar dot A. And we figured out that the scaling for these guys is lambda squared 1 lambda. And we said that that was nice because we could put them together with a derivative and have a covariant derivative, which I wrote in terms of momenta just to sort of emphasize. So I feel like this is a momentum space. That these guys have the same power counting in the different components. Okay, and so when we come and talk about gauge invariance, this fact that they have the same power counting in the different components will, of course, be important, because what gauge invariance does is ties momenta to gluons. And we'd like, if we didn't have the same power counting in the different components, then we would not have a gauge field corresponding to certain momenta. Okay, so another way of arguing that this would be they should have the same power counting would have been directly from gauge invariance. All right, so I'd like to continue there. The one thing that you'll note, which is unusual from an effective theory point of view, is there's a set of fields that have no suppression at all. These AN minus gluon fields just scale like 1. So when you have dimensional power counting, all the fields have dimensions. You add more fields, you get higher dimensions, you get suppression. Here, with this lambda power counting, there's a component of the gauge field that has no suppression. We can add as many of them as we want, and that costs nothing. So let's do that and see what happens. So a priori, you might think that this is really bad because you could have an infinite number of different operators at lowest order just with a different number of these AN minus fields. And we'll see that actually things are not so bad. But I think it's best to do that by way of an example. So we'll consider an example that just has one collinear particle in it for simplicity. And we can do that by having a heavy particle that carries a lot of energy decay to a light particle, like a B quark decaying to an up quark. So in QCD, your current would just be U bar gamma B. Gamma would be left-handed current. And we can consider the B quark to be an HQET. And we have an energetic U quark, is what we want to consider. It's not the only possibility, but we could pump all the momentum out through the current into the leptons, into the E nu, but let's pump energy into the up quark so that it's energetic. So here's the current in QCD. B goes to U. And the notation that I'll use for this is a double line for the H heavy quark, and then a dashed line for the collinear quark. So this guy is going to be described by an HV field. This guy is going to be described by a CN field. This is production, so this will be a CN bar. So I'll reserve this notation of dashed lines for collinear quark field, for collinear quark propagators. Okay, so the simple-minded thing is just to write down an effective theory current where I replace the full theory fields by the effective theory fields. I replace the up quark by an up quark that's a CN, collinear field in some direction. And I replace the heavy quark by an HV for the B quark. And then effectively that would be the tree level matching between this diagram and that diagram, or the tree level matching from that particular diagram. But let's consider adding these AN minus gluons, since they were things that we could add to the current. So we can add any number of AN minuses here, and we'd have something that's the same order in the power counting. So let's consider another diagram in QCD, where I just attach an AN minus gluon, and I'll attach it to the heavy quark. So I have a different number of external fields, but this one costs me nothing when I go to the effective theory. Let's call this momentum here K. We'll call this guy here Q. And this guy here we'll just say is MBV. So then K is MBV plus Q. And I can write Q out in components since it's a collinear particle. If I want to identify the big piece, then that would be the m bar dot Q piece. So remember last time from looking at coordinates, we can write out any vector in terms of the coordinates, and it's useful to do that since the coordinates have a different power counting. Now what's going to appear in the propagator here is k squared minus m squared minus mb squared. So let's look at k squared. So if I square this term, I just get mb squared. If I square this term, I get 0. But then there's a cross term as well. And then there's some dots, and the dots are indicating terms that are suppressed. And so if I look at k squared minus m squared, then that's m dot v, mb, m bar dot q, and this is order lambda to the 0, since the momentum n bar dot q is order lambda to the 0. So there's no suppression in the propagator. There's no power counting to the propagator. And that really, another way of saying is this propagator is off shell by a hard amount. Okay, these scales are hard, and if I go back to my picture, that means they're up here in this purple region. Put a purple box around this. Okay, so the degree of freedom, which is this purple propagator, is actually living up in that purple region. It's something we have to integrate out. Okay, so let's do that. So integrating it out just means expanding the diagram, and I've already expanded the propagator, so there's the denominators. Just have to expand the numerator. Okay, so we have our, let me write out A and mu. Let me replace the spinner by the field. And I'll start by just writing in the full propagator, and then we'll start expanding it. I'm using a convention here for the gluon interaction in QCD, which is plus I, G, TA, gamma mu. Okay, so there's the full theory, and all I've done is take the full theory, and rather than write spinners and a polarization vector, I've just written the fields, because I'm, in the end, interested in looking at what kind of operator I get. So I'm interested here in taking the piece which is not suppressed. So let's just do this slowly. So there's an index A on this guy as well. So let's write out the leading order piece of the numerator. I've collected some i's, put the G out front. So if I take all the order 1 pieces of the numerator, then these are the order 1 pieces. MB is order 1. K I can replace by MBV plus Q. And then there's a MBV slash that's order 1, and an N slash over 2 N bar dot Q. That's the same decomposition we had over there. Here, because I'm interested in a certain polarization, let me pull out that polarization. Then I have my denominator. And my denominator we already expanded, so let's just write that in. Okay, so far so good. So this piece here is 0, because n squared is 0, n slash squared is n squared. So then we have this piece. For this piece, we could 1 plus v slash, remember, is part of a projector that could act on the heavy quark. But there's this n slash in the way, so we want to push it through. So we can do that. So let me write out the 2 pieces from pushing it through. There's an MB that cancels this MB once that term's gone. So let me do that. When I push it through, I switch to 1 minus v slash. There's still a 1 over n dot v here. And then there's an hv. And 1 minus v slash on the heavy quark field is 0. And then the n dot v cancels the n dot v. So if I want to write this, putting now this AN field inside because the TA is inside, then write it like this. So the momentum here, n bar dot q is order 1, and this n bar dot an is order 1. So this operator is the same size as this operator here. And that's what I was saying, that we should worry about, the fact that we can add these gluons without any cost. And we just added one and found out that we have an operator that's the same order. So the way you might draw this, and there's a convention also for collinear gluons where you put a line through them. So this is a collinear gluon. Is that this guy is the same order as this guy. OK? Well, we'll come back to this and talk more about it in a minute. Let's consider another diagram. We attached the gluon on the left. Let's also attach it on the right, see what happens. So again, QCD diagram. Doing the same thing, attaching the gluon here, some Q, this is some momentum P, and this is then P minus Q. This case is different than the previous case. The reason that this case is different is that both P and Q are collinear. And so P minus Q is collinear too. Same scaling as P and Q. So this propagator is not off shell. In our hyperbolas, it would live on the blue hyperbola that I drew, which is well within the effective theory, not outside the effective theory. So we don't want to integrate out this propagator here. And what that means is that there'll be, in the effective theory itself, an interaction, a Lagrangian interaction that takes into account this diagram. So in the effective theory, if you like, if I draw an effective theory diagram, there will be an effective theory diagram that allows us to attach that gluon, because this propagator here is a propagator in the effective theory. Unlike the one that I just erased, which was off shell and had to be integrated out of the effective theory, this one is inside the effective theory. OK. So adding on the left does something different than adding on the right. On the add on the left, we knock the quark off shell. When we add on the right, it's close to mass shell. So we can consider generalizing what we just did by adding more gluons. Remember that we don't have any restrictions on how many we can add, so let's just consider adding more. Let's add m of them. And I'll call the momenta Q1, Q2, through Qm. And all these propagators here are off shell. This is a QCD graph. When I calculate graphs like this, if I have these gluons there, I have to also consider cross diagrams. So let me just write, rather than trying to draw cross diagrams, let me just write plus cross gluon graphs. And what you would expect from what we said before is that in the effective theory, this is going to match onto some kind of Feynman rule that looks like this, but then has a bunch of gluons that can come out of the vertex. In this case, m of them. OK, that's what we expect. And so we expect a generalization of this operator with m fields rather than just one. So if we do this calculation, it actually turns out to not be too complicated. I can include all the cross diagrams by sum over permutations. I have one of these n bar dot a gluons for each external gluon line with a corresponding color factor. And I'm always just getting these order 1. I keep the largest piece of the denominator, and I'm always just getting the order 1 momenta. And there's a slight complication that when I have a graph like this, if I look at the momentum of this, it's q1. But if I look at the momentum of the next one, this would be q1 plus q2. And so the denominators here are not just simply q's, but sums of q's. OK, and these n's would be dotted into fields, and t's would be dotted into fields. So if we want to write this as an effective theory operator, then we should think about what this vertex means in the effective theory. And we should be a little bit careful, because what this means, if you think about it, is in terms of the locality of this diagram, is that all these gluons are coming out of the same point. So it's like phi-4 theory, where you divide by 4 factorial. You have to be a little bit careful, because any one of these gluons, from the point of view of the external states, is equally good as an attachment. So when we put in the gluon fields, we ought to be careful about those factors. So this is the right Feynman rule. And one way of just thinking about it is we'll have m of these fields, but then we'll divide by an m factorial. OK, so we can write down the complete result for the tree-level matching as an operator. Since we just calculated all the diagrams. So we started with this current with QCD, and we matched it at tree level onto a current that I can write like this, hiding all the complexity in this thing I call W. I have to sum over however many attachments, which I was previously calling M, but now I'm calling K. And if you study this guy for a while, actually what is true is that this guy has a name. This is a momentum space Wilson line. So what is a position space Wilson line? That's where it really looks more like a line. So a Wilson line is a string of gauge fields that goes between 2 points, here between -infinity and 0. There's some ordering to the fields because they don't commute, because they're not abelian. And the fact that it's a line means that we go in a straight line between the 2 points. So here's a path which is a straight line, S, between -infinity and 0. And actually this formula here is the Fourier transform of this is giving you the Wilson line that I drew up, the Feynman rule that I drew up there, or the fields that I drew up there. So there's some ordering to the fields, and what this P does is it orders the fields in the appropriate way. Namely, it puts the guys with the larger argument to the left. So on your homework, you're going to do the exercise of thinking about doing this matching for 2 gluons, and taking the Fourier transform of this and connecting these. At least I believe that's what I asked. That's a very good exercise to see everything work out that I'm just describing to you here in words. So one way of thinking about what's happened in this effective theory, and this actually turns out to be generically true, is that rather than having this n bar.a field, which was order 1, it actually can be traded for this Wilson line object. Okay, so I just showed you that that happened for this particular example, but it turns out actually to be generic, that instead of talking about the n bar.a field, we can talk about this function of the field, which is this Wilson line. Leave that for a sec. So this is true in this operator. We just got this Wilson line. In terms of the Wilson line, things are pretty simple. And it actually turns out to be generically true, and we'll see that later on. So the way that you can, and we'll also talk about gauge invariance later on, which has to do with this story. It turns out that this Wilson line can also be understood from the point of view of gauge invariance. The need for this Wilson line can be understood from the point of view of gauge invariance. And I can at least describe that to you in words. So if you look at this diagram here, we can't attach collinear gluons to this quark. But this quark carries color. We can attach collinear gluons to this quark. No problem, doesn't knock it off shell or anything. So we're going to have a problem with gauge symmetry because we have 2 things that are colored. A priori, we're going to have a problem with gauge symmetry because we have 2 things of colored, one of which we can't attach effective theory fields to, and one of which we can. But there's also hot operators with gluons in them, which are these ones. And what effectively happens is that the gauge transformation that would used to be for this heavy quark field, it gets moved into this Wilson line. So there'll be this Wilson line will transform in a way that compensates for the transformation of this linear quark field. And that's exactly because the gluons here, which were kind of the corresponding gluons in QCD for the gauge transformation, are explicitly integrated out to give that Wilson line, so it's all tied together. We'll come back and talk about that in more detail later.